Okay, hello and welcome to the 11th live session on signals and systems. My name is Avik Mukhopadhyay and I am a PhD student at the Department of Electrical Engineering at IIT Madras. So today we'll be looking at some sample problems and the primary topic would be DTFT, which stands for Discrete Time Fourier Transform. So far we have explored the continuous time Fourier transform and Laplace transforms, but mostly in the continuous time domain. So today we'll be jumping to the discrete time. Okay. Okay. So I'll share the questions. Yeah. So we have the first question on the screen. So it says that if the discrete time Fourier transform DTFT of a discrete time signal x of n is capital X of e power j omega, then the DTFT of x of n minus n naught is what? So if you are familiar with the property of Fourier transform, then this should be straightforward to you. And so here what has been asked essentially is that if you shift the original time domain signal in time domain by some n naught amounts, then what is the change that gets reflected in the Fourier transform? And in this case, in the discrete time Fourier transform, because we are dealing with a discrete time signal, right? Or discrete time sequence. Sometimes the word sequence is also used, especially in the context of discrete time. So the correct answer straight away should be option B here, right? Because uh, I mean option B and D are identical here. I think there is a typo here. But the main thing is that if we shift by some amount in the time domain, then in the frequency domain we have a multiplicative factor of a complex exponential, right? So there will be a multiplicative factor of e power minus j omega n naught. Okay. So anyways we shall derive it. So but the same observation was made in the context of continuous time Fourier transform as well, right? So let us see. So my original signal x of n, the discrete time sequence, has okay, I think someone wants to join. Okay, Abhinaya, can you hear me? And can you see the screen? You can unmute and respond. So is the screen visible? Is my audio fine? Yep. Okay, anyways, I shall continue. So as I was saying, x of n has a DTFT which is given by capital X of e power j omega. So this is one of the notations. You can find other notations like x of j omega or x of simply omega like this in various textbooks. But since this is the notation that has been followed in the actual lectures for this course, I'll stick to it. And here, as you can see, this is capital omega, and this is not the same as the omega that we study in the continuous time. Okay, in the continuous time Fourier transform, that was small omega, and the relation between small omega and capital omega is that capital omega equals to small omega into capital T. So this capital omega is like kind of unitless, dimensionless, or you can say it's in radians, because this omega is in either per seconds or radians per second, and we also have this T here which is seconds. So overall it is like radians, which is not really a unit actually. So this is the difference between the two frequencies. Okay, so now this is known to us, this is the DTFT pair. Now in our question it is asked like, if I have x of n minus n naught, then what is my DTFT? Okay, that is the question. So any thoughts, like what should be the answer? Yeah, so let us actually derive its DTFT. So the DTFT of my shifted signal x of n minus n naught is what? Okay, before that let us first revise the actual formula of DTFT. Okay, how is the DTFT given? Capital X of e power j omega is equal to summation. Of course we will encounter a summation because it's in the discrete domain, discrete time domain. In continuous time domain we have integral, right? So summation x of n e power minus j capital omega n, and the index of summation is n, running from minus infinity to infinity. This is the DTFT. Okay, this we have seen in the lectures. Let me label this as equation 1. Now what is the DTFT of the shifted input x of n minus n naught? From the above definition of DTFT we can write this as summation, instead of x of n now I have x of n minus n naught. The rest of the things are the same, e power minus j omega n, and my summation runs from, the index is n, running from minus infinity to plus infinity. Now in these kind of summations, in order to simplify, we usually follow a substitution method, right? So I'll substitute this parameter inside the brackets, which is n minus n naught, with some variable. Okay, so let my n minus n naught be some other variable small m. Okay, so this is the assumption, this is the substitution that we are making. Okay, so that means that your small n is m plus n naught. And now once we do such kind of substitution, we also have to take care of the limits, upper and lower limits. They will also accordingly change, right? So initially my variable was small n, which was varying from minus infinity to plus infinity. Now my variable is m. So now m will vary from, as n varies from minus infinity to infinity, m will vary from minus infinity to infinity, because m is nothing but n minus n naught. So you subtract like n naught, which is some finite quantity, from infinity, doesn't really make a change, right? So the upper and lower limits still remain the same. So now what I will do is, from here, So this summation I can rewrite as my new variable is small m, which runs from minus infinity to plus infinity, and x of n minus n naught gets replaced by x of m times e power minus j omega. Now I can replace small n by m plus n naught. Okay, m plus n naught. Okay, so now I have summation in the power, so I can express is this as the product of two exponentials. So this becomes summation m running from minus infinity to infinity x of m e power minus j omega m times e power minus j omega n naught. Okay, okay, this is basic algebra. E power x plus y is nothing but e power x into e power y. That's what I am doing. Okay, so now what do we have here? Okay, now our variable is m. Okay, the index of summation is small m. Now this term here, as you can see, e power minus j omega n naught is completely independent of small m. So this term is independent of small m, which is my index of summation. So I can bring this factor outside the summation. So if I bring this outside the summation, I have this. Okay, now you can hopefully already identify the form. We are back to the original form of the DTFT. So now we can do a last step, which is not really necessary, but just for completeness, we can actually now replace this variable small m by small n. Okay, just a change of variable doesn't really change the mathematics. So instead of m, I am just using small n. Okay, what I am doing is changing variable from m to n. It's just a change of name, that's it. Okay, now what about this whole thing here, this summation? This is known to us, right? This is exactly the DTFT of x of n. See, from equation 1, this is exactly matching with equation 1, right? Capital X of e power j omega. So this whole thing is exactly capital X of e power j omega, which is my DTFT. And how can I write this? From equation 1 basically, right? So overall what do I have is minus e power minus j omega n naught. This is my multiplicative factor that I have, times capital X of e power j omega. Okay. This is my modified DTFT of my shifted input. Okay, so therefore the conclusion is that if x of n has DTFT given by capital X of e power j omega, then x of n minus n naught will have a DTFT given by e power minus j omega n naught times capital X of e power j omega. Okay, so we have actually derived the time shift property of the discrete time Fourier transform. Okay, we have seen the similar result in the continuous time case as well. So here just we have capital omega instead of small omega. Okay, okay, now actually if you compare with the options, and I think there is a typo, as I was saying, both option B and D are identical here. So both of them are actually correct. So answer option B, D. Okay, both are same actually, but I think one of them had to be a different one, right? Otherwise it's just redundant. Okay, all right, so moving on to the next one. So what is the DTFT? So this is question number 2. What is the DTFT of a discrete time signal x of n given by the summation delta of n minus 8 plus delta of n plus 8? Okay, so we have the sum of two shifted delta functions. Okay, canonical delta, right? So this, we have to recall the definition of the delta function. Okay, so one way to approach this problem is, okay, the naive approach is to actually compute its DTFT. That's fine, using the formula, that's fine, but the form here is that we have two shifted delta functions, right? Sum of two shifted delta functions, and just now in the first question we have derived the time shift property of our DTFT. So we observed that if x of n is shifted by some amount n naught, then we have a complex exponential e power minus j omega n naught as a multiplicative factor sitting in front of the DTFT, right? So if we know the DTFT of our delta of n, then we can also directly know the DTFT of delta of n minus n naught, let's say, any shifted version of delta n from that property. And in this case we have exactly that form, right? We have delta of n minus 8 and delta of n plus 8 added together, and from linearity we can actually combine them, right? So that is the method that I am going to follow here. Okay, and by this time you should be familiar with the DTFT of delta of n. So the DTFT of delta of n is exactly 1. Okay, so but if you are still not convinced, then I'll just show you in just one line. So this is question number 2. What we are given is this signal x of n is delta of n minus 8 plus delta of n plus 8. Okay, and what is its DTFT? And just to give you a recap, the delta of n here is this function. The definition is as follows. So delta of n takes the value 1 when n is exactly equal to 0, and it is taking the value 0 for all other values of n, and n here is the time index in discrete time, right? So n takes all integer values, it cannot take any fractional value, so it is 0 otherwise for all, let's say n, for all other integer values of n other than 0. Okay, plus minus 1, plus minus 2, plus minus 3, and so on. Okay, so this is the definition. So now if I want to use that time shifting property which we derived in the first question, I have to first know the DTFT of delta of n, because the function here x of n in this question is given in terms of, expressed in terms of delta of n, right? Shifted version of delta of n. So what is DTFT of delta of n? From the definition of DTFT, I can compute its DTFT as summation delta of n, which is my signal whose DTFT I want to compute, times e power minus j omega n. N is running from minus infinity to infinity. Okay, this is the definition. Now what does this evaluate to? Basically, if I run this summation all the way from minus infinity to infinity, there is actually going to be only one term which is going to survive, corresponding to n equals to 0. Just from the definition of delta of n, I am saying this. Because delta of n is non-zero and it is equal to 1 only for n equals to 0. So that is the only term in this summation that is contributing to some value. Rest of all the values would be 0, right? Because delta of n for all other n would be 0. So this is exactly equal to delta of 0 times e power minus j omega into 0. Delta of 0 is 1 and this factor here is 1 again, so this is equal to 1. Okay, so we just verified once again that delta of n has a DTFT which is equal to 1. Okay, now we are almost done, because now we will straight away utilize the property that we derived in the first question. So if delta of n has a DTFT equal to 1, then delta of n minus 8, let's say, has a DTFT given by, let's go back to that property, x of n minus n naught has a DTFT e power minus j omega n naught times x of e power j omega. So this property. So let's apply this here. So we will have a factor of e power minus j omega into 8 times 1, which was our original DTFT. So how I am writing this? From the property that we derived in the solution of question number 1. So from the result of question number 1. And similarly, delta of n plus 8 will have a DTFT e power j omega into 8 to 1. And again, this is the same. So now overall, if we combine these two, if we add these two, then what is my DTFT? It will also be the sum of their individual DTFTs, right? Which follows from the linearity of DTFT. So I have e power minus j omega 8 plus e power j omega 8, and this is by linearity of DTFT. So this now, as you can see, is a sum of two exponentials, and if you remember the relation between the sinusoids and the complex exponential, remember that cos theta was given by e power j theta plus e power minus j theta by 2, and sin theta is given by e power j theta minus e power minus j theta by 2j. Okay, j is the square root of minus 1. So here the form of the DTFT is actually almost similar to the cos form, right? It's actually 2 times cos theta, because it's the sum of those two exponentials. So here theta is actually 8 omega, right? So this becomes 2 times cos of theta, which is 2 times cos of 8 omega. Okay, this is my required DTFT, and if I check with the options, it is option A. So my correct answer is option A. Alright, now moving to the third one. Okay, so in the third question, we are asked that if x of n is real and even, then what can we say about its DTFT, capital X of e power j omega? Okay, whether it will be purely imaginary and odd, whether it will be purely real and even, purely imaginary and even, purely real and odd. So four different combinations are given. Which one of them is correct? Okay. Okay, so this is also kind of a property which should be known to you. But anyways, we'll derive it from scratch. So now let's start with the third one. Okay. So what we are given is that x of n is real and even. So two information is given to us, real and even. So first of all, x of n is real, and which means that okay, it is purely real number, right? So if I take its conjugate also, it remains the same. So the conjugate of x of n is exactly equal to x of n since it is purely real. So I can write one condition which is x star of n is equal to x of n. So here star denotes the complex conjugate. Okay, so this is first equation. So I'm calling this equation 2 because I've already used one equation 1 previously. Okay, fine. So I have one condition. Now on top of this, I have also been mentioned that x of n is even. So even means it's not that it is taking even values, because this is the context of a signal. We are studying signals and systems. So whenever we encounter the word even, in the case of a signal, it means that it is an even signal or an even symmetric signal, as we have seen, right? We have seen the definition. So it means it satisfies the condition x of minus n is equal to x of n, right? So it is evenly symmetric about the vertical axis. Okay, so whatever you have on the negative side of the vertical axis will be exactly a mirror image of what you have on the positive side of the vertical axis. Okay, so for example, the cos theta function, it's an even symmetric function, right? X squared is an even symmetric function, and so on. So from the second condition, x of n is even or even symmetric. Let me for completeness write this as even symmetric, implies that from the definition of an even signal, x of n is equal to x of minus n. So I'll call this equation 3. Alright, so now let me go to the next page. Okay. Now we have to comment about the nature of the DTFT. So regarding its real or conjugate nature, like complex nature, and um, regarding its even or odd symmetric nature. So first of all, from the notation, we have that okay, x of n has a DTFT which is given by capital X of e power j capital omega. This we know, right? This is the DTFT pair, and I'm calling this as equation 4. And from the definition of DTFT, the formula is as follows. This. Okay, so now before commenting about the DTFT, given that x of n is real and even, I'll first like to know that if I have a signal x of minus n, then what is its DTFT? Okay, so let us find out. I mean, this is just the time reversal property of DTFT. So what is the DTFT of x of minus n? From the definition of DTFT, I know that I'll have this summation and again, like the last time we used the substitution, I'll do here as well. So my n was running from minus infinity to plus infinity, so m, which is the new variable, will run from plus infinity to minus infinity. But since we are summing it from the lower limit to upper limit, the exchange of the limits doesn't really matter much, because regardless of whether you sum from the left side to the right side or from vice versa, like the result remains the same. So this now becomes summation m running from plus infinity to minus infinity x of m e power j omega m. Okay, okay, now it is still not exactly in the form of the DTFT formula. To arrive at that form, I can make certain modifications. So first of all, as I was saying, the you can actually exchange the upper and lower limits of the summation here, uh, because I mean here actually both the upper limits and lower limits are the same, just with a difference in uh, sign. Okay, so ultimately the result will be the same if you exchange those limits. So what I will do is I'll exchange the upper and lower limit. So m running from minus infinity to infinity, it still remains the same, x of m, and now I am writing this term here as e power minus j minus capital omega into m. Okay, so now this is in the form of the DTFT formula, right? With the only exception that the frequency now here has been flipped in the sign. So instead of capital omega, I have minus omega. So this is capital X of minus e power j omega. Okay. So this corresponds to that the frequency has been flipped. Okay. So x of minus e power j omega. Okay. So we just derived that x of minus n has a DTFT given by capital X of minus e power j omega. Okay. And now in our example, in this question actually, I know that x of n is even, right? So x of minus n is the same as x of n, and we have actually captured that in one of the equations as well, this third equation here. So x of n is exactly equal to x of minus n because it is even symmetric. So from here I can also write that x of minus n is the same as x of n. So x of n also has a DTFT, which is capital X of minus e power j omega, and this is coming from equation 3. Okay, and this whole observation I'll capture as equation 5. Okay, Now what I will do is I will compare equation 4 and equation 5. So what do they say? So equation 4 is like the standard DTFT pair, like x of n has a DTFT capital X of e power j omega, and equation 5 that we just derived also tells me that x of n has a DTFT which is capital X of minus e power j omega. So both of them, if we compare, we can claim that the RHS should also be equal, right? So x of e power j omega should be equal to x of minus e power j omega. Okay, so by comparing equation 4 and equation 5, we get capital X of e power j omega is equals to capital X of minus e power j omega. Okay, so what does this tell us? See, this is in the frequency domain, discrete frequency domain. So we have an even symmetric nature in the in the discrete frequency, right? So this means that x of e power j omega, which is our DTFT of the original signal, is even symmetric. Okay, so regarding the symmetry of the DTFT, we have now reached to the conclusion that it is even symmetric. And what I can do is I can actually capture this in the form of equation 6, let's say. Okay, so one part is done, and now you can actually eliminate some of the options. So you see, whichever option contains the odd symmetricity, you can actually eliminate them. For example, option A and option D can be eliminated now. Okay, the only thing you need to confirm is whether it is going to be option B or option C. So for that, you have to now check whether whether the DTFT is going to be real or imaginary. Okay, so now let us do that. So as we derived the DTFT of x of minus n, now what I will do is I want to know what is the DTFT of the conjugate of x of n. Okay, so as you can see that I am actually not directly writing the form, I am actually deriving it for the sake of completeness. So that will help you as well. So let us try to find the DTFT of x star of n. So what is the DTFT of x star of n? That is nothing but summation n running from minus infinity to infinity x star of n e power minus j omega n. So this is um, how can you write this? This is basically summation n running from minus infinity to infinity x of n, this whole thing inside the summation I'm trying to rewrite this in another form. So I'm trying to get rid of this conjugation here. So for that I'm rewriting this as this. So this is still the same because what I am using here is that if I have two complex number, let's say z1 and z2, their product is there. So if I take the whole conjugate of this product, then it is simply z1 star into z2 star, the product of their individual conjugates. So this is exactly what I am using here. So e power j omega n will have a conjugate e power minus j omega n, right? So once you take this conjugate inside, then you will have a product of their individual conjugates, which is exactly the form in the previous step. Okay, so now and now I can use linearity, so I can actually take the summation inside as well. So this is x of n e power j omega n whole conjugate. Okay, because what I am doing here is that if I have summation um, zi star, okay, say I running from summation over I, this is also the same as summation zi over I, the whole conjugate. Okay, all this follows from linearity. So now I will again adjust for a negative factor in the power of the exponent, in the power of e, so that I have e power minus j some frequency into n, that form, right, which matches with the DTFT form. So I'll write this as x of n into e power minus j to minus capital omega into n. Okay, whole conjugate. Now the term inside the bracket is exactly your DTFT but at the negative frequency. So x of minus e power j omega, and I have a conjugate as well. Okay, so we just derived that x star of n, the conjugate of x of n, has a DTFT given by x star of minus e power j omega. Okay, and now I already know that x of n is real, right? It is purely real. So if even if you take its conjugate, it still remains the same. So x star of n is the same as x of n. So in the LHS above, I can actually replace x star of n by x of n. So that has a DTFT, which is x star of minus e power j omega. And this, in fact, we had captured in one of the equations as well. It was equation 2. Yeah. See, x star of n is equal to x of n, which follows from the fact that x of n is purely real. So this line follows from, this step actually follows from equation 2. Okay, and overall this relation, this DTFT pair, I will label as equation 7. And now, like previously I compared the two equations, I will now again compare equation 6 and 7. So let us go back to equation 6. Here is equation 6, which dictates the even symmetricity of the DTFT. Now in equation 7 we have this relation, right? Or rather what I will do is I will compare. Okay, from equation 7 what can we see? We can see that x of n has a DTFT which is given by this capital X star of minus e power j omega. Okay, and now from the basic DTFT formula we know that x of n has a DTFT capital X of e power j omega. That's the known relation. So that means that this x star of minus e power j omega, whatever we have on the RHS of equation 7, should be matching with the actual DTFT, right? Capital X of e power j omega. So what I am saying is I will compare equation 4 here, which is the basic DTFT pair, right? So I will compare equation 4 with equation 7, and their RHS should match actually. So that way, so by comparing equation 4 and 7, we get x of e power j omega equals to x star of minus e power j omega, right? Their RHS are the same, because same, if the signal is same, it will of course have the same DTFT, right? So by comparing their RHS, we can come to this conclusion. So I'll mark this as equation 8. Now what I will do is I will again compare this equation 8 with equation 6. See, this was the equation 6 which actually captured the even symmetric property of x of e power j omega. So I already had capital X of e power j omega equal to capital X of minus e power j omega from equation 6. Now I am also having a form from equation 8 that capital X of e power j omega is equal to capital X star of minus e power j omega. So I can compare these two, the equation 6 and 8, to get capital X of minus e power j omega is equal to capital X star of minus e power j omega, right? So I have just compared their RHS. So this, now we can make a change of sign simply from minus omega to plus omega, and we can rewrite this as capital X of e power j omega is equal to capital X star of e power j omega. So what is the observation here? Capital X of e power j omega is exactly equal to capital X star of e power j omega. So even if you take its conjugate, it's still the same. So this entire capital X of e power j omega, which is actually the DTFT of your original signal x of n, is purely real. Okay. So this means that capital X of e power j omega is purely real. Okay, so now we are done with the second part as well. So initially we observed that the DTFT is even symmetric regarding the symmetricity. Now we just also came to the conclusion that the DTFT is also purely real as well. So overall we can combine these two to claim that capital X of e power j omega is real and even symmetric. So both real and even, and it is exactly option B. So the correct answer is option B. So this is just one property which we uh, discovered now. So if x of n, the signal, discrete time signal, is real and even, then its DTFT will also be real and even. Okay, so you can remember this. Okay. All right, now moving to the question number 4. We are given a discrete time signal x of n equal to minus 8 to the power n times u of n. And for this signal, we have to determine the DTFT. Okay. All right. So let's just do this. So question number 4, we have x of n equal to minus 8 to the power n u of n, and we have to figure out the DTFT of this signal. So let me denote it by the standard notation, capital X of e power j omega. Okay, this is what we need to find. Okay, and from the formula of DTFT we know that capital X of e power j omega is given by summation n running from minus infinity to infinity x of n e power minus j omega n. Okay, now x of n in our question is this signal minus 8 to the power n into u of n. So this is nothing but summation small n running from minus infinity to infinity. I can replace x of n by minus 8 to the power n into u of n. This. Okay, now we have the term u of n in our signal. So u of n is the unit step function, right? In the discrete time unit step function. So u of n takes the value 1 whenever n is greater than or equals to 0, and u of n is 0 whenever n is less than 0. And n is the index for discrete time here, so it takes only integer values. So this essentially actually lets us to get rid of the negative indices of n, because here we don't need to actually run the summation all over from minus infinity to infinity, but we can actually rather consider only the non-negative side, that is from n running from 0 to infinity, because my u of n would be 0 for the negative side. So the summation from minus infinity to minus 1 won't contribute to this summation, it will vanish. So I can actually replace the lower limit of summation by 0, n running from 0 to infinity, and in this range only my u of n will take the value 1, non-zero. Okay, so I'll replace u of n by 1 times e power minus j omega n. So this is following from the definition of u of n, because u of n, as we know, is equal to 1 whenever n is greater than or equals to 0, and it is 0 when n is less than 0. Okay. Okay, now I can club these two terms together actually inside the summation as follows. So both have small n in the power, right? So I can uh, first of all I can take this negative sign outside the summation, and I'll have 8 into e power minus j omega whole to the power small n, right? Okay, and what is this giving us? So this is, I have negative sign outside, And if I split this summation, then I'll have, like, if I evaluate this summation, okay, first is at n equals to 0 it will be 1, at n equals to 1 it will be 8 into e power minus j omega, then 8 into e power minus j omega whole squared, and so on all the way till infinity. So this is exactly infinite GP series, right? Sum of infinite GP series. So, and we know uh, the formula, right? Okay. Okay, I think there is some typo here in the question, because I guess it should be some number less than 1. It can be zero point 0.8, I think. I think somehow it is, although it is stated as 8 here, but I think it should be a number less than 1, because this is the summation that we are having here. But this infinite summation will converge only when the common ratio, the multiplicative factor, its absolute value is less than 1. Then only it converges, right? So in this case, its absolute value is greater than 1, right? Because the common ratio here is 8 into e power minus j omega. Its absolute value is 8, which is like more than 1. So it will keep on growing as you sum up all the way till infinity. So what I will do is, I think it should have been zero point 0.8. Okay, so what I'll do is, I'll change it. Okay, I'll change this in the question as well. So this is minus 0 0.8. Okay, minus 0 0.8 whole to the power n into u of n, and whatever else was there, yeah, minus 0 0.8 minus 0 0.8 0 0.8. Okay, so these terms here would be 0 0.8 e power minus j omega, then 0 0.8 e power minus j omega squared, and so on. Okay, so now this we know. Now this is like, this will converge because the absolute value of the common ratio is actually zero point 0.8, so which is less than 1, right? So this will converge, and we know that uh, its summation is given by the first term divided by the first term minus the first term divided by 1 minus the common ratio. So for example, if you have a series like a plus a into r plus a into um, r square n into r cubed and so on all the way till infinity, then its summation is given by a is the first term, 1 minus r is the common ratio, provided mod of r is less than 1. Okay. So this will give us minus, the minus sign is outside, so 1 by 1 minus 0.8 e power minus j omega, and the same as 1 by 0.8 e power minus j omega minus 1. Okay, so this is the DTFT. And actually, yeah, so the same correction has to be made in the option as well. So I think option C is having the same form, okay, except for that 8 has to be replaced by 0.8. So I'll still mention option C as the right answer, but I'll make the modification later. Okay, all right. Fine. Now coming to the fifth question. So let me make a note. I have to correct for this one. Okay, so what were the changes that we had to make so far? This was one change. Another, I think, typo was the option of question number 1 as well. So both options were identical, right? So but that's not a big issue. You can consider that as a multi-correct MCQ maybe. Okay, but yeah, question 4 was having a error in the data, so I'll modify it. But question 5, let us now move to question 5. Okay, so as you can see that we have actually so far looked at examples, as well as we have derived certain properties of DTFT uh, in each of these examples. So, and likewise in the fifth question that we are going to solve now, again we will going to be deriving another property. So we are having a discrete time signal y of n, which is given by n times x of n, and we have to find its representation in frequency domain, which means we have to find its DTFT basically. So and as you can see that the options are given in terms of capital X of e power j omega, so which is the actual DTFT of x of n, but the signal that you are taking here is n times x of n, which is y of n, and you are trying to evaluate capital Y of e power j omega, which is the DTFT of y of n, and that has been expressed, that has to be expressed in terms of capital X of e power j omega. Okay, so let us see how we can do that. So y of n is given by n into x of n, and in our question we are asked to find the DTFT of this signal basically, capital Y of e power j omega. So this is the standard notation that we have been following so far. So this is what this is asked in the question. Okay, so capital X of j omega, which is the DTFT of x of n, is given by summation n running from minus infinity to infinity x of n e power minus j omega n. This we know, right? Now what I will do is I will differentiate both sides with respect to omega. So differentiating both sides with respect to capital omega, we get okay d omega of capital X of e power j omega on the LHS is equal to d omega of this whole summation here. Okay. Now what I will do on the RHS here is that this derivative is a linear operation, so I can take that inside the summation here. Okay, and once I take that derivative inside the summation, I have a factor which is x of n, which is simply the time domain signal, which is independent of my frequency omega, right? So x of n is totally independent of capital omega. So my derivative will effectively act on this factor inside the summation, which is e power minus j omega n. Okay, so I'll take the derivative inside and actually take the derivative of this term inside, okay, which is e power minus j omega n. So okay, let me move to the next page. So from here we are getting that d omega of capital X of e power j omega. This is the LHS, but on the RHS what we have is we are taking the derivative inside the summation. So x of n is unchanged and I'm taking the derivative of the second term here, d omega of e power minus j omega n. And this is nothing but summation n running from minus infinity to infinity x of n. What is the derivative of this term? So it is equal to e power minus j omega n times minus jn, right, from the chain rule of derivative. So this is minus jn into e power minus j omega n, and then I can write this as, this is my LHS. Okay, now what I have here, I have a factor minus j here, which I can bring outside the summation because it's just a constant independent of n. So minus j comes outside and I have summation n running from infinity, minus infinity to infinity, n into x of n. So I'm pairing this n and x of n together. Okay. And I have e power minus j omega n as well. So now notice here, what is this n into x of n? This is exactly my y of n, right? The actual signal which is given, y of n, right? So this is actually my y of n. So what I have here is minus j is outside, summation minus n running from minus infinity to infinity y of n into e power minus j omega n. And now this is exactly matching with the form of DTFT, because this whole summation here is actually the DTFT of y of n, so which is capital Y of e power j omega. So this is minus j into capital Y of e power j omega. So the derivative of the DTFT of x of n is giving me minus j into the DTFT of y of n. So now I can actually express capital Y of e power j omega in terms of capital X of e power j omega. So what I have here is capital Y of e power j omega is equal to, so I have to divide by minus j on both sides. So 1 by minus j will give me uh, plus j actually, because j square is minus 1. So this gives me j into d omega of capital X of e power j omega. So this is what the DTFT evaluates to. So my property that we derived here is that if we multiply the signal x of n by n, it's like a multiplication in time domain, and I'm multiplying it by the time variable itself. Then I have a differentiation derivative in the frequency domain. Okay. So this is my y of e power j omega. This is the frequency domain representation of n into x of n. And this is actually matching with option B. So the answer is option B. Okay. So hopefully this is clear. Okay, now let us look at the sixth question. Again, we have to find the DTFT of this given signal. So this signal is also somewhat related to the unit step function, but its form is slightly different. So it's a product of three terms, as you can see: n plus 1 into alpha to the power n into u of n. Okay, you can use property here as well, but to use the property you have to know what is the DTFT of alpha power n into u of n. Okay, so although we have looked at an example, which is example 4, we have looked at minus 0.8 to the power n into u of n and calculated its DTFT. Here also, like, similar form is there, alpha power n into u of n. That also has a standard known form of DTFT, but I'm not solving that. It's straightforward. I'm not solving that because that happens to be one of the questions of the assignment. So yeah, but we can anyway solve this using the direct formula. Okay, so let us do that. Okay, so in sixth question, basically what I was saying is, so you can solve this in multiple ways. So x of n is given as n plus 1 into alpha to the power n into u of n. This is given. Okay, now what I was saying is, okay, you can write this as n into alpha power n into u of n plus alpha power into u of n. Okay, I'm just splitting this summation. Now once you know what is the DTFT of alpha power n into u of n, okay, let's say something like whatever, you can use some any variable. Okay, let's say z of capital Z of e power j omega. Let's say you know this. Then what do we have? N into alpha power n into u of n plus alpha power n into u of n will have a DTFT given by, so what is the first term here? N into alpha power n u of n. So alpha power n into u of n has a DTFT z of e power j omega. So I am multiplying by a factor of n, and just in the fifth question we have seen the effect of multiplying by n uh, results in derivative, right? J times the derivative of the uh, DTFT. So this first term here will have the DTFT given by j times d omega of z of e power j omega, plus for the second term I will have simply z of e power j omega, right? Okay, so but for this you have to have the knowledge of z of e power j omega. Okay, uh, so you can try this way as well, but or else we can simply just go by the formula and evaluate its DTFT, which I am going to do in this case. But you can try for this way also, because I think in one of the questions of the assignment you have to actually find this DTFT of alpha power n into u of n. That is why I am not solving that. Okay, so maybe you can do this as a homework. Okay, okay, so meanwhile you can think and parallelly solve it. Okay, so So yeah, but in this case we are going to just follow the naive approach using the formula, okay? Because I don't want to directly solve the assignment question, which are yet to be, submitted for grading. So here, let me start afresh. So this is n plus 1 into alpha power n into u of n, okay? And you're trying to find the DTFT of this signal. So using our standard notation, we will denote the DTFT as capital X of e power j omega. Okay, this is what you are trying to find. And also, which is required, you are given that, of course, I mean, u of n is the typical standard notation for the unit step function, is the in the discrete time here. And also we need the condition that absolute value of alpha is strictly less than 1, because as we saw in one of the examples, that it has to converge, right? We'll have a summation, infinite summation, and that will converge only if that common ratio of the GP series has an absolute value which is strictly less than 1. So we need this condition mod alpha less than 1, okay? For that has to be bounded. So this is given, mod alpha is less than 1, and we know that u of n is the unit step function. And what is the definition? It is 1 whenever n is greater than or equals to 0, and it is 0 whenever n is less than 0. So now, what is my capital X of e power j omega? So capital X of e power j omega from the definition of DTFT is as follows. This, so we have seen this so many times by now. So now what do we have? I am just substituting x of n by the function which is given in this summation. So I have n plus 1 into alpha power n into u of n to e power minus j omega n. Okay. Okay. And again, now I can actually modify the lower limit of the summation like we did before in one of the examples, because I have u of n inside the summation. So effectively, my summation can run from 0 to infinity, because then only in that range u of n is 1 and non-zero. For n less than 0, u of n is simply 0, and the sum will be 0 actually. So there will be no contribution to the summation for the negative portion of n. So this I can rewrite as summation n running from 0 to infinity, n plus 1 into alpha power n into 1, because u of n is 1 in the non-negative region, so into e power minus j omega n. And this I can also slightly modify, not really modify, but like as we did before. So I will club these two terms together, alpha power n and e power minus j omega n, because they have this common n in their exponents. So therefore I will pair them together. So I have n plus 1 into alpha e power minus j omega whole power n, right? And let me call this as some capital S. Let's say this sum evaluates to some capital S. We need to find capital S. Okay. Okay. So what is capital S? Capital S is this summation small n running from 0 to infinity n plus 1 into alpha e power minus j omega whole to the power small n. Okay. So now if you evaluate this summation, what do you get? So what do you get here? If you put n equals to 0, what do you have? 1 into alpha e power minus j omega whole to the power 0 plus, on putting n equals to 1, we have 2 into alpha e power minus j omega plus, on putting n equals to 2, we have 3 into alpha e power minus j omega squared, and similarly it's 4 into alpha e power minus j omega cubed, and so on. It will run all the way till infinity. Okay. So what am I having here is, so this first term is basically 1 because I have 1 times something raised to the power 0, which is also 1. This is 1 plus 2 alpha to the power minus j omega plus 3 alpha e power minus j omega squared plus 4 alpha e power minus j omega cubed, and so on. Okay. Let me label this as equation 9 because so far I think the latest equation was marked as equation 8, right? In one of the previous examples. Yeah, I think this was the last equation that we used, equation 8. So now I can number this by equation 9. So I'm just following a sequence. Okay. So now what do we have here? You see, the summation is 1 plus 2 into alpha e power minus j omega plus 3 into alpha e power minus j omega squared plus 4 into alpha e power minus j omega cubed, and so on. So there is kind of a pattern in this. So you see, although you have a multiplicative factor of alpha e power minus j omega in all the successive terms, but it is not really a GP series because my coefficient here in front is also changing, as you can see, or rather it is increasing, right? It is increasing like 2, 3, 4, and so on. Okay, if this would not have varied from 1, 2, 3, and 4, so on, then it would have reduced to a simple, infinite GP series. So here it is like a combination of both GP as well as AP series, because here these terms, the constant term here in front is growing as an AP from 1, 2, 3, 4, and so on. So the next term would be 5 into alpha e power minus j omega to the power 4, and so on. So the multiplicative factor or the common ratio for the GP portion is alpha e power minus j omega, whereas there is also a AP portion here, and the common difference for that is 1 because it is growing by 1 step, 1 unit. So this type of progression is known as a arithmetico-geometric progression. Okay, and there is a way to solve this when you have like infinite number of terms, and what we do is we take the common ratio of the GP portion. So as we saw that the multiplicative factor, the common ratio of the GP portion is alpha e power minus j omega here. right? So I will multiply this summation s by that factor alpha e power minus j omega, and then I will shift each term to the right by one step. Okay, so why I am doing that will be clear in a moment. So what I am doing is I am multiplying alpha e power minus j omega with this, which is my the common ratio of the GP part. So that is equal to, now I am writing everything by shifting one place to the right. So this one here gets multiplied by alpha e power minus j omega, but I am writing it slightly by shifting to one step to the right. So this becomes alpha e power minus j omega plus, now this 2 into alpha e power minus j omega gets multiplied by alpha into e power minus j omega. So that becomes 2 into alpha e power minus j omega squared, and then I'll have the successive terms. So this will be cubed. Okay, this is cubed, and so on. And let me call this equation 10. So now hopefully you can observe why I wrote it in this form. So now what we can do is we can simply subtract these two equations. Okay, on subtracting equation 10 from equation 9, what do we get? So on the LHS it becomes like s minus alpha e power minus j omega into s. So I can take 1 minus alpha e power minus j omega as common. This whole into s is equal to, now let us subtract them term by term. So I'm subtracting equation 10 from 9. So here I will have 1 minus 0, right? Nothing is there. So that gives me 1. Then I have 2 alpha e power minus j omega minus alpha e power minus j omega. So which gives me plus alpha e power minus j omega. Similarly, 3 minus 2 will give me 1 for the squared term. And in this way we have eliminated the AP portion, as you can see. So now it is only growing geometrically, okay, till infinity. So from a arithmetico-geometric progression, we have reduced this to a purely geometric progression, which we know how to find the summation because we have an explicit form for the summation. Okay, so what do we have? 1 minus alpha e power minus j omega to s is equal to, so what about this whole thing on the RHS? This is the infinite GP series, and as we have seen, its formula is given by a by 1 minus r, where a is the first term and r is the common ratio of the GP series. And this converges clearly because the common ratio is alpha e power minus j omega, right? And if you take its absolute value, that gives you alpha, okay, sorry, which is not alpha, it is absolute value of alpha into absolute value of e power minus j omega. That's basically 1, right? Because e power minus j omega is like uh, a circle of radius 1 in the complex plane, so its absolute value is always 1. Or you can think of it as, you know, cos omega plus j sine omega, and if you take its modulus, it will always be square root of cos square omega plus sine square omega, which is 1. So that portion will always be 1. So effectively it is mod of alpha, and in our question it is already given that mod of alpha is less than 1. Okay, that's why we needed this assumption for this summation to converge, and that is why this converges to 1 by 1 minus alpha e power minus j omega. And so I can bring this factor on the right side, which will give me s equal to 1 by 1 minus alpha e power minus j omega squared. Okay, so this is my s, and this s was simply my just a dummy variable for my capital X of e power j omega, right, which is the desired DTFT which I wanted to calculate, right? So my x of, therefore my x of e power j omega is this s which we calculated, which is 1 by 1 minus alpha e power minus j omega squared. Okay, and if you check with the options, it is exactly matching with option C. So the correct answer is option C. Okay, all right, so with this we have covered all the questions for today's session. And yeah, I will just correct the options in this question number 4, right? We needed this convergence, that's why it can be 8 here, so I'll replace it by 0.8. But yeah, so we have covered a lot of concepts, primarily centered around the DTFT. So we have looked at many properties, derived them, looked at examples, and yeah, drawn some important remarks. So hopefully you will keep this in mind, and let us stop at this point, and we'll meet again on next Monday 6 p.m. and probably that will be the last and final session of this live session. Okay, so thank you. I'll sign off.